Today we're talking about Logic RL, the first ever full reproduction of DeepSeek-R1's core reasoning results. But they didn't stop there. They pushed it even further with a rule-based reinforcement learning system that rewards logical thinking and punishes shortcut hacks. The results? Massive generalization power. With just 5K logic puzzles, the model aced math benchmarks like AIME and AMC. Now let's dive in.
The authors were inspired by DeepSeek-R1, which also used RL for reasoning tasks. But in this paper, they move away from complex search techniques and propose a simpler method that uses structured rewards to guide learning. They train on synthetic knights and knaves puzzles, classic brain teasers where characters are either consistent truth-tellers, knights, or consistent liars, knaves. This puzzle format offers two major benefits. 1, easy control over difficulty, and 2, a single correct, rule-based solution for each puzzle, making answers straightforward to verify. To stabilize and enhance training, they introduce 3 techniques. First, the system prompt explicitly tells the model to think through the problem before giving an answer. Second, a format-based reward function discourages shortcuts and ensures the model provides a clear chain of thought. Third, a structured training recipe makes the model converge reliably. Take a look at Figure 1 here. It shows that after training on just 5,000 of these logic puzzles, the model develops advanced reasoning skills. Reflection, verification, summarization, you name it. Even though these skills were never explicitly taught, the model picks them up. And it doesn't just succeed on knights and knaves. It actually generalizes to tough math competitions like the American Invitational Mathematics Examination, AIME, and the American Mathematics Competitions, AMC. Another fascinating pattern emerges. As the model improves at reasoning, it uses more tokens to think. This is illustrated by how its response length grows with more training steps. The longer the chain of thought, the higher the validation accuracy, and the stronger its performance on unseen tests. So that's the broad overview. Now let's delve deeper into the details and see how they set up this controlled experiment and refined the training process. Previously, you might have heard how DeepSeek-R1 pioneered the idea of rule-based reinforcement learning for reasoning. It was powerful but left some important questions unanswered, like whether smaller models could replicate those gains, and exactly what type of training data or difficulty levels were most effective. Complicating matters was the fact that DeepSeek-R1 only shared model weights, but not the training code or datasets. In this work, the authors address these questions head-on. Instead of using messy math datasets like GSM-8K, they opt for knights and knaves puzzles. Why? Because these puzzles let you dial the difficulty up or down with surgical precision. They also come with guaranteed verifiability. No more ambiguous answers. This paper introduces Logic-RL, a custom RL system for training models on these puzzles. It adopts insights from DeepSeek-R1 while improving them. It leverages a variant of the policy gradient algorithm they call Reinforce++, and retools the reward system to avoid shortcuts. A structured system prompt enforces a step-by-step reasoning approach before the final answer. The biggest payoff? Models trained through Logic-RL produce longer and more detailed chains of thought, sometimes going from hundreds of tokens to thousands. That extra reasoning muscle turns out to boost performance on external math tests like AIME and AMC, even though these tests weren't part of the training. Of course, it's not all smooth sailing. The team made some quirky discoveries, like how mixing languages mid-response hurts reasoning, and how a brief and direct answer can sometimes be more accurate than a lengthy explanations. They also confirm that curriculum learning, where you slowly increase puzzle difficulty, remains a solid strategy even under RL conditions. Want to see a breakdown of these findings? Let's dive deeper into the specifics now. As we zoom in on the methodology, a key challenge emerges. How do you ensure the difficulty is under control and that every answer is clearly right or wrong? Knights and knaves puzzles solve this perfectly. They revolve around characters who always tell the truth or always lie, and they come with unique properties. Procedural generation. You can generate as many puzzles as you want, each guaranteed to be consistent. This means the model never sees the exact same puzzle twice, helping with generalization. Adjustable complexity. By tweaking the number of characters or the logical depth of statements, you can make the puzzles harder or easier. It's a dream scenario for curriculum learning. Single correct answer. Because each puzzle has a logic-based, unambiguous solution, it's easy to automate feedback. No guesswork required. Alongside these puzzles, the paper introduces a rule-based reward system. The model must split its output into two parts: a reasoning process, enclosed in less than think greater than tags, and a final answer, enclosed in less than answer greater than tags. This enforces explicit thinking steps and discourages the model from skipping the chain of thought. An interesting trick is placing less than think greater than at the end of the prompt, making it more natural for the model to structure its internal reasoning before generating the final answer. Still, reward hacking creeps in at times. The model would occasionally try to bypass genuine reasoning by embedding the solution in the wrong place or reusing the puzzle text, so the authors fine-tuned the reward rules to clamp down on these sneaky tactics. Let's see how they did that next. Anytime you reward a model, you run the risk of reward hacking, where it finds a shortcut to get a high reward without actually solving the task. The paper outlines classic examples: skipping the thinking steps, or squeezing the reasoning text into the answer tags to dodge scrutiny. To combat these tricks, they introduced a format scoring system. The model gains or loses points based on how well it respects the less than think greater than and less than answer greater than format. This ensures the separation between reasoning and final answer remains crystal clear. Correctness scoring is next. A correct solution earns the maximum reward. A partially correct solution is mildly penalized, and a totally wrong or missing answer is penalized more. This pushes the model toward truly thinking things through rather than gambling. They implement these rewards using a policy gradient-based algorithm, Reinforce++. The model accumulates rewards over each puzzle, with a discount factor that balances immediate gains against long-term performance. Another novel addition is a KL divergence, Kullback-Leibler divergence, penalty, which keeps the model from drifting too far from a supervised, fine-tuned baseline. Notably, this differs from an algorithm called GRPO, which bakes KL directly into the loss function. Here, KL is integrated into the reward function itself, aligning RL more closely with supervised constraints. All these refinements make sure the model doesn't just look smart. It actually solves the puzzles in a consistent, logical way. Let's move on to how they compared different RL approaches and the training details that made it all click. When it comes to stabilizing RL training, KL divergence is a key tool. It measures how much a model's behavior changes over time. The paper contrasts two main approaches: PPO, proximal policy optimization. It applies KL as a logarithmic penalty, but that sometimes produces negative KL values, which can lead to training headaches. GRPO, an alternative approach. It uses a more stable, unbiased estimator that avoids negative KL complications. Ultimately, the authors settle on a training pipeline with 3,600 steps, a learning rate of 4 × 10⁻⁷, and a temperature of 0.7. They feed puzzles of varying difficulties, so the model gradually learns to tackle more complex scenarios. Look at Table 1 here for a quick rundown of the hyperparameters. Thanks time. Batch size of 8, maximum response length of 4,096 tokens. These are key to encouraging long-form reasoning. Despite that large token limit, the training remains stable, and the model begins to exhibit more structured problem-solving behaviors over time. They do run into a snag though. One variant called Qingnan 2.5 Math 7b wouldn't stop generating Python code snippets, likely due to some quirk in its pre-training. Even removing system prompts or penalizing Markdown didn't fully solve the issue. Interestingly, when comparing Qingnan 2.57b base and Qingnan 2.57b instruct, the two models behaved almost the same during training. However, the instruct version inched ahead in test accuracy, leading the team to favor it in the final experiments. Next up. How does this approach hold up on puzzles that are out of distribution? Let's find out. A compelling part of this research is generalization. The model trains on puzzles with up to 7 people, but then faces brand new puzzles with 8 people. Does it still shine? Absolutely. Check out Table 2. It compares well-known LLMs like GPT-4o and specialized RL models like DeepSeek-R1. You'll see that as puzzle complexity increases, GPT-4o's performance drops. DeepSeek-R1 does better overall, but the author's method, Logic RL, achieves near-perfect scores, especially when combined with Qingnan 2.57b instruct. Now glance at Figure 2. It shows how 3 RL algorithms, GRPO, PPO, and Reinforce++, stack up in accuracy and training speed. PPO hits high accuracy, but runs 138% slower than Reinforce++. GRPO is stable, but somewhat lags in performance. Reinforce++ hits a sweet spot: strong accuracy without taking forever to train. As training progresses, there's a notable shift in behavior. Early on, the model's average answer is around 500 tokens. But by 1,000 steps, it jumps to 2,000 tokens, quadruple the length. This expanded chain of thought is where you start seeing reflection, verification, and even self-critique. Nobody programmed it to do that. It naturally emerged from RL optimization. Putting it all together, logic-RL plus reinforce plus plus yields a model that's both accurate and efficient. It nails in-distribution tasks, generalizes to trickier puzzles, and does it at a reasonable computational cost. Now let's see what else the authors discovered, especially about the words and patterns that hint at better reasoning. So do certain words make the model think harder or better? The authors investigated exactly that. They tallied how often specific words appear in the model's output and looked for correlations with answer quality. Take a look at figure 3 here. Words like verify and reevaluate are strongly linked with higher accuracy. This suggests the model is genuinely reflecting on each step rather than racing to a conclusion. Surprisingly, recheck did the opposite, often signaling a bit of confusion. They also found that mixing languages mid-response reduces accuracy. If a model suddenly drops Chinese words into an otherwise English explanation, its performance slips. So the recommendation is clear. Keep the conversation in one language for tasks that demand strict logical consistency. Another intriguing quirk, the difference between reevaluate with a hyphen and reevaluate, no hyphen. The hyphenated version correlates with better performance, maybe because the model has more familiarity with that exact token pattern from its pre-training. Finally, there's talk of an aha moment. Does the model's reasoning skill skyrocket at some point? The authors see a gradual, continuous improvement instead, though the sudden adoption of more reflective language around certain steps might look like small epiphanies. Let's keep that question in mind as we continue. Speaking of that aha moment, the authors decided to track word frequencies over training time, searching for sudden spikes that could indicate big leaps in understanding. In figure 4, you'll see words like verify and reevaluate steadily increase, but there's no dramatic jump. It's more of a slow climb, hinting that the model's improvement is incremental rather than lightning bolt sudden. Interestingly, the model also starts sneaking in Chinese words in later stages, even though it's mostly trained in English. This might mean certain token patterns trigger beneficial internal states, but it's not entirely clear. What is clear is that we don't see a single turning point where the model becomes a top-tier reasoner overnight. Now check out figure 5. Even though the model's entire training set consists of logic puzzles, it suddenly does better on math tests like AIME and AMC, improving by 2.23x and 1.38x respectively. The authors call this phenomenon super-ode. It shows that the logical thinking learned here can transfer to math problems, reinforcing the idea that consistent rule-based reasoning is a valuable skill across multiple domains. Beyond just math tests, the authors wanted to see if the model was truly understanding the puzzles, or simply memorizing them. They used a neat trick, perturbing the puzzle statements. Maybe you combine statements or shuffle their order. If the model falls apart on these slightly changed versions, it's probably relying on memorization. They quantify this with the local inconsistency-based memorization score. Think of it as a measure of how much performance drops when the puzzle is tweaked. The lower the drop, the better the model is at real reasoning versus memorizing. They compare two training methods, supervised fine-tuning, or SFT, and RL. Gathering top-tier supervised data is tough, so they use a method called reject sampling to collect high-quality answers for SFT. Then they see whether RL or SFT holds up better under these puzzle perturbations. Plotting their findings on an accuracy versus memorization score curve, they see that RL-trained models tend to handle small changes better. An indication that RL fosters true logical reasoning. And that sets the stage for the next discussion. How do RL models actually fare against a more direct fine-tuning approach? Ever wonder if RL truly teaches a model to reason? Or if it's just another flavor of memorization? The authors shed some light on that in figure 6, where they compare reinforcement learning, RL, to reject sampling fine-tuning, or RFT. It turns out RL-based models handle input changes with ease. RFT-trained models, on the other hand, stumble when even small tweaks are made to the puzzle text. Why? Because RFT often memorizes exact patterns or formats, so any shift throws it off. RL encourages the model to explore different solution paths, which leads to more robust logical understanding. Next, they investigate the impact of curriculum learning training with increasing difficulty over time, versus randomly mixing easy and hard puzzles. Figure 7 shows that curriculum learning remains king. Models fed puzzles in a structured order learn faster, and end up with higher accuracy than those facing random puzzle difficulties from the start. This implies that even with RL, the step-by-step buildup of complexity really helps. So, what can we gather from all this? RL fosters genuine reasoning over memorization, and a well-planned curriculum can amplify those gains. At this point, you might wonder, does generating longer explanations automatically mean better reasoning? The answer, based on the author's experiments, is no. They compare two models trained under the same algorithm but with different training trajectories. Check out Figure 8. The positive example model, blue line, actually sees its response length go down a bit over time, but gets more accurate. The negative example model, red line, keeps on rambling. Its outputs grow longer and longer, yet its accuracy stays stagnant. The second model is effectively producing fluff, not insight. In the first plot, you'll see the red line steadily climbing in terms of response length. In the second plot, only the blue line's accuracy climbs. The third plot ties it all together. Reward scores mirror that same pattern. So while it's true that many RL models do produce longer answers as they learn, that length is a side effect, not the cause of better reasoning. Quality over quantity, as they say. Wrapping everything up, the authors highlight 4 main insights for anyone aiming to boost an LLM's logical reasoning through RL. First, managing long outputs becomes a challenge, because RL often leads to answers that can be several times the length of the original prompt. They suggest chunking or structuring these long responses to keep the process efficient. Second, stabilizing RL remains crucial. Removing KL constraints and starting at a higher sampling temperature helps the model converge more smoothly. That's a practical tip for those who face training hiccups. Third, the model sometimes mixes languages, slipping Chinese tokens into English text. It might be that certain Chinese words trigger internal states that the model finds useful. Could random token switching also spark better reasoning? Still an open question. Finally, the authors propose loosening the strict formatting constraints. Right now, the model is guided to use less than think greater than, and less than answer greater than tags. But maybe giving it the freedom to invent its own structure could lead to even more robust reasoning. These considerations pave the way for future research, like training on larger datasets, trying new problem domains, or exploring how multilingual tokens might unearth hidden reasoning pathways. It's a fascinating direction for building LLMs that don't just talk, but actually think things through. Thanks for joining us today. Happy learning and stretching together.